Hello everyone, this is Physics 103. This is on nuclear physics, and in this lesson we are going to learn about nuclear binding energy. So inside the nucleus you have a proton and a neutron. So suppose you have a, a separate proton and a neutron first. So they are not bound into a nucleus yet. So a proton has a mass approximately 1 atomic mass units or 1 U. For the neutron, its mass is also approximately equal to 1 atomic mass units. So if you combine them inside the nucleus, so for example, you bring them together and make them into one nucleus, so one proton and one neutron, so you would expect that in the nucleus their mass should be 1U plus 1U, so 2 atomic mass units. But experiments show that inside the neutron, the mass of the proton and the inside the nucleus, the mass of the proton and the neutron combined is not equal to their individual masses combined. So in other words, their sum is less than their parts. So if you weigh this nucleus, it is less than 2 atomic mass units. So where did all the mass go? If we are to be consistent with conservation of mass. So here comes nuclear binding energy. So when the proton and the neutron combined inside the nucleus, some of their mass is converted to energy, particularly binding energy. So this stems from Einstein's idea that there is equivalence of mass and energy. So how do we calculate how much binding energy is needed to combine a proton and neutron? So if you want to find the binding energy, we need to get the amount of mass that is lost, because energy is converted in mass is converted into nuclear binding energy. So let's write an equation. So this binding energy, let's write it EB plus the mass of the combined proton and neutron. Let's write it as mass of the nucleus itself. So you have combined protons and neutrons in A and the number of protons in Z. Of course, if this is energy, the first term is energy, we should multiply this to C squared. So to be consistent with energy. So this is equal to the individual masses of the protons and neutrons. So you have here mass of the proton times the number of protons, Z, plus mass of the neutron times the number of neutrons, N. Of course, we should also multiply by C squared. So this balances out the individual masses or energies, if you like. So you can think of this as the individual case wherein the proton and the neutron are not together inside the nucleus, and this is the binded or how do you call it? Bounded by binding state, wherein the proton and the neutron is combined together inside the nucleus, and there is an extra energy needed to combine them. So isolating EB, we have equals, let's write Z MP plus N Mn, and then subtract the actual mass of the nucleus. So MAZ all over multiplied to C squared. So this formula will give you the binding energy of the nucleus.